Okay, hello everybody and welcome to this week's lecture. Remember that last week we were looking at solvable and nilpotent, or for the last couple of weeks we were looking at solvable and nilpotent Lie algebras. And they had lots of ideals. In principle, they had lots of ideals given by these the derived series, or more specifically the central series. This week we're going to be looking at something that's somehow opposite to this, or at the other extreme, something that has very few ideals. Okay. So that's the general idea to think about. We're breaking Lie algebras into different families or different types depending on how many ideals they have, roughly speaking. Okay. So let's just start. Let's start here, just following on that thought. We say that a Lie algebra is simple if it is not abelian and it does not contain ideals except for 0 and L. Okay, so no ideals. At the other extreme to something which is solvable, which will in general contain ideals, maybe even many ideals. If you look at the abelian condition here, that is not that restrictive actually, because if you see if it has dimension 2 or greater than, and it's abelian, then it will contain abelian ideals. Clearly, any dimension, any subspace, any linear subspace will be an ideal because the thing is abelian. So really, and that would contradict the second part of the definition. So really what abelian is excluding the zero Lie algebra and the one-dimensional. There is only one-dimensional Lie algebra. So it's excluding those two cases. So we could, if we wanted to, actually replace abelian by dimension greater than or equal to 2. But that's not how people do it in general. It looks a little bit ugly, so we put in abelian. But just remember, it's only excluding these two possibilities. Now, we want to, next, we go to semisimple, so we weaken this a little bit. And we say that L is semisimple if it does not contain abelian ideals except 0. Okay, not ideals, but abelian ideals. So it's definitely weaker. We see that simple clearly does imply semisimple. We'll come to this later on. We'll recall this again later on. But you can see that simple is in fact semisimple because we're asking that it contains no abelian ideals except 0. Well, simple contains no ideals except 0 and L, but L is excluded because it's assumed not to be abelian. Okay, so it's a generalization where we change from ideals to abelian ideals. Next, this third one, which doesn't seem to obviously follow from the other two, we'll spend a lot of the lecture explaining why this is the case, is that Z is equal to the radical. Okay, this is the center. It's going to be all of those elements that basically whose Lie bracket with any other element is 0. And the radical, you remember, the radical is the maximal solvable ideal. We want that two of these things are equal to each other. So just to help you with this, let's just recall some facts from last week. Remember that, as I said, the radical is going to be the maximal solvable ideal. So what you do is you take the linear span of all of the all of the solvable ideals inside in L, and this is again an ideal, and it's solvable. And by construction, basically, you can see that it's maximum. The center. Remember that the center, the set of abelian elements is the center of elements whose Lie bracket or any other element is 0. This is an ideal, clearly, and moreover, it's solvable because the first, if you take the derived series, the first term in the derived series is, of course, going to be 0 because Z is abelian. Hence, it's solvable, and hence it's contained inside in the radical. Okay, and this inclusion here, which is easy to see, is going to be very central to the lecture. And what this third guy here, what reductive is asking is that this is not an inclusion, not just an inclusion, it's in fact an equality. Okay. So how this can be understood as a generalization, a weakening of this property and a turn of this property, that's what we'll be doing over the course of the next couple of slides. Okay. So if let's note first that if a Lie algebra L contains a solvable ideal, then L contains an abelian ideal J, which is contained inside an I. So here, just to be clear, J is an ideal. It's an ideal in I, but it's something stronger. It's actually an ideal inside an L. Okay. So if you and in particular, if we let I equal to L, these two things are the same. We see that every solvable Lie algebra contains a non-trivial abelian ideal. Okay. How do we show that? Well, we're just going to use the definition of solvable. We're going to take the derived series. So if we let I be a solvable ideal, then there will exist an n greater than 1, such that I of n, bracket n, is equal to 0, and I to the n minus 1 is non-zero. And moreover, we have that the Lie bracket of this ideal with itself is equal to I to the n 0 is equal to 0. Okay, just remember that the definition of solvable is that this derived series eventually terminates. But what does this mean? Well, it means that I to the n is a non-trivial, it is non-zero here by assumption, is a non-trivial abelian ideal of L. Okay. And this is our non-trivial abelian ideal. So just to be clear here, you should remember from the earlier lectures that we're using, so why we see from this that I to the n minus 1 is actually abelian. This is clear. But why is it an ideal inside in L? Well, because of the way it's constructed. So basically, if you have two ideals inside in a Lie algebra and you take their Lie bracket, then the Lie bracket is again an ideal. And that's how we've constructed these things. Okay. So we've constructed the first term in the derived series of L is just going to be the Lie bracket of I is going to be the Lie bracket of I with itself. This is the Lie bracket of two ideals inside an L, hence the first term is going to be an ideal inside an L. And then we iterate it again. The second term is going to be constructed. It's the Lie bracket of two ideals, well, one ideal with itself. So that's again an ideal inside in the larger space inside an L, and so on and so on. So eventually we know that this guy here is actually an ideal, which is to say all of the terms inside in this derived series are going to be ideals inside in the larger space. All right, so solvable always contains an abelian ideal. Now that's of interest to us because we defined semisimplicity in terms of abelian ideals. So this allows us to express semisimplicity in terms of solvable ideals, as we now see. So let L be a Lie algebra. We claim that the following conditions are equivalent. L is semisimple is equivalent to L not containing any solvable ideals except 0. And that in turn is equivalent to the radical being equal to 0. Okay, so by the lemma above, if L contained a solvable ideal, then it would contain an abelian ideal, and that would contradict our assumption of semisimplicity, because semisimplicity requires that there are no abelian ideals except 0, no non-zero abelian ideals. Okay, and the assumption of a solvable ideal would imply the existence of such an ideal, so it can't happen. Now we have to go the other way. 2 implies 1. So we recall that any abelian ideal is automatically solvable. Hence, if L does not contain any non-zero solvable ideals, then it cannot contain any abelian ideals. Okay, because abelian are solvable. So, going back here, we see that these two things are not the same. We could basically go back and change the definition of semisimplicity to require no solvable ideals, and nothing would change. We would get the same objects. but it's better to have the weaker, it's better to have the condition that looks at least weaker, because there's less to check when you're trying to verify that something is actually semi-simple. But the moral is that replacing a abelian ideal with solvable ideal in the definition of semi-simplicity doesn't do anything. And that all really comes from the previous lemma, where we show that any solvable ideal has got an abelian sub or an abelian ideal. Okay, and then the last one is actually clear. It's that the radical is the largest solvable ideal of L, and abelian ideals are solvable. So if the radical is 0, then L must be semi-simple. Okay. Remember that your center is going to be contained. It's not the best way of looking at it. Yeah. Okay. I think this is clear. Okay. If we have no, yeah, it's clear. Okay. So that's 3 different ways of looking at semi-simplicity: abelian ideals, solvable ideals, and the radical being equal to 0. Let's put that in a table. So this is basically a very good way to remember what we proved in the previous slides. We have normally, for a general Lie algebra, we have this inclusion. We have an inclusion here. But these 3, simplicity, semi-simplicity, and reductiveness, they require, all of them will need that the center is equal to the radical. For the first 2 guys, the center would be equal to the radical, would be equal to 0. For semi-simplicity, this is equivalent. For simple, simple needs more. Simple implies this equality, but this equality does not imply simple. Simple is a stronger condition than this. But now we see that the way they were previously defined, simple, semi-simple, and reductive seemed a little bit of a strange one. These 2, this was clearly a generalization of this, and this seems like it didn't belong so much in the definition. But now we see that it actually does if we express it in these terms. Now it's clear that if something is simple, then it satisfies this, therefore it satisfies semi-simplicity. And then this is a weakening again, because we're requiring just that these 2 things are equal and not that they're equal to 0. So this is a very important picture for understanding the definition of simplicity, semi-simplicity, and reductivity. And then we just summarize here in this slide what I said before. Simple implies semi-simple implies reductive. Okay. A corollary of this observation is that if L is abelian, then it is reductive. Okay. Let's leave this for a moment and just concentrate on the proof of this. If L is abelian, then we know that L, the whole Lie algebra, is equal to the center. That's the definition. But then this has to be equal to the radical, because this is contained, the center is contained in the radical. We have an inclusion here. So if this is equal to everything, then there's no room between the center and the Lie algebra itself for the radical to live. So the radical has to be equal to L. Which is to say that L is reductive. Okay. So this is reasonably easy. But then we come to this comment here. It basically, abelian are very special, very, very easy, some of our examples. And they satisfy, that means they're both solvable and reductive. So something can be solvable and reductive at the same time. Okay. Maybe, for example. Okay. One thing you might see is that semi-simple seems to suggest that the Lie algebra is kind of almost simple. It's not clear so far what the how much of a generalization semi-simplicity is, or how these things really relate, because we've just got this inclusion here. It's yeah, and in fact, this is what we'll be showing in later part of the lecture. Is at least in the case where the Lie algebra is finite dimensional, we'll be able to see that there's actually a simpler way of looking. Simpler, sorry if you don't mind me using the word, simple, to describe semi-simplicity more directly in terms of simplicity. But this is what's coming later. But a remark here is really for this section, for definition of these three things, just remember this identity here, this inclusion, I should say, sorry, and then requiring equality of these things and a relation to zero. That is what simplicity, semi-simplicity, reductivity is all about. It's all about this inclusion here. Okay. Okay, so now that we have our notions of simplicity, co-semi-simplicity, and reductivity, we have them defined at an abstract theoretical level. In practice, however, if you want to verify these conditions for some Lie algebra that you're given, they're not always that useful. It's not so easy to verify them in practice. So what we would like is a more practical collection of tools that in the real world, which is to say looking at examples, can be used to verify semi-simplicity. So something that's actually more practical to verify. We're going to do that in two ways. One is going to be through representations, and the other is going to be through bilinear forms. So a bilinear form in Lie algebra is just a bilinear form with respect to the vector space structure of L. And they're going to be, in particular, we're going to be most interested in special types of bilinear forms. Three types in particular, when I recall the definition. Before we do, for bilinear forms here, assuming that you're all familiar with inner products and vector spaces, that's very good to keep in mind, the analogy here at least. And you'll see from your experience with inner product spaces, you'll see a lot of the same things carrying over, okay? So we say that a bilinear form is symmetric if we can swap the two entries, swap x and y to yx, and it doesn't do anything. The bilinear form doesn't see a swap. Okay, it's symmetric. Again, the obvious analogy with in the definition, one of the requirements of the definition of an inner product. Another one, which is again, let's skip on to the third one. So for an inner product space, for an inner product, we also had non-degeneracy, which was that if you put any element in, if any element paired with every other element of the vector space to give you zero, then you knew that that element actually had to be zero. And here you see the definition carries over non-degeneracy directly. Okay, so we say sigma of bilinear form is non-degenerate if for all x in L, we have that sigma of xL is equal to zero if and only if x is equal to zero. Okay. The if is obviously trivial because it's a bilinear form. But yeah, it's the only if is where the requirement is. Now, the middle one here is, well, let's take a little bit more time to look at this. If we start, and sorry, there's a typo here, there should be a Z as well, an L, I guess it's clear what's going on. So what we have is we have three elements, X, Y, and Z. And we're trying to let our bilinear form act on these, but it's a bilinear form, so it only has it can only take two entries. But we have three, but we want to still let sigma act upon these three elements. What do? Well, we take the other piece of information we have, the fact that we're dealing with a Lie algebra, and we sort of collapse. We take the product of these two here, the product of these two using the Lie bracket. And this gives you an element of your Lie algebra. So now you've got this element, and you've got Z, two elements. Hence, the bilinear form can actually act upon them. This is well defined and makes sense. Now, another option we have is we can take these two elements here and we can take the Lie bracket of those, the Lie bracket of the Y and the Z, and then let sigma act on X and this new element. That's another perfectly reasonable way. There's no preference here. There's no reason why doing it on the first or doing it at the start or at the end should be different. So these two ways, somehow I guess this is a common thing in mathematics when you have two different ways of carrying out a process that you want to carry out. Oftentimes you don't want them to give you two different answers. You want it to give you the same answer in both cases. And this is what's going on here. We're basically saying it doesn't matter if we do our trick of taking the Lie product on the start or at the end, it's going to give us the same thing. Now, another way of looking at it is, let's see, maybe I can write a little bit here, is sigma of, this is going to be minus the adjoint. Oop, I don't know how, hopefully this is legible, of X. Okay, and Z. That's what's here. And this should be equal to, this is what the requirement is, X of add Y of Z. Okay, so it's sort of looking like, for when you have an inner product, you can take this operator and bring it over to the other side at the cost of a minus. So it's kind of like an anti-unitary operator. So if you want to think about it in terms of inner products and operators and inner product spaces. That's also what's going on, whichever way you prefer. But anyway, whatever happens, this is the definition, and there it is. So, your drawings, and we move on. So, if we have a bilinear form, what can we do? Well, if you have the bilinear form, let's forget about the L invariance for the moment. Okay, if you have a bilinear form, then you can always construct the space here, the perp, which is just going to be all elements in L, such that they're perpendicular, which is just a way of saying that when you put them into the bilinear form, every other element inside in the ideal, you're going to get 0. So it's almost, I mean, if you think about, let's say R2, the X and Y plane, and then if you look at the real line and you take the standard inner product, the perp is just going to be the X-axis or the Y-axis. The X and the Y are going to be perpendicular to each other. And this is basically an analogy. This is what we're doing here. We're taking an ideal and we're looking at all the elements that are perpendicular. Okay. You do not need L invariance here to actually define this. But what L invariance does give you is that this thing here is an ideal. Okay. So I leave this as an exercise. And I leave you to think about the fact as well, whether or not the Lie algebra is going to be equal to the direct sum. So maybe I can. Okay, of the ideal and its part. Then you put a question mark here. You should try to, this is something good to think about. Maybe I can put this even as an exercise as well. Okay, so bilinear form, it allows us to construct perps. Clear this again. Now the question is, bilinear forms, fine. We've defined them. They've got these properties. If it's L invariant, then it gives us a means of constructing ideals from ideals. But how do you actually construct bilinear forms in general? Well, they come from one way of constructing them is from representations. So if we have an L representation, then consider this. Sorry, this should be a product, not a comma. It's the product of two matrices inside and. So use the representation. This gives us here a linear operator on our vector space V. Okay, that's what a representation is. It takes your Lie algebra, maps you into the linear endomorphism ring of this space. Same for Y. Now here, again, sorry, this should just be a multiplication, which is composition of operators inside the endomorphism ring of V. We can take the composition, that gives us a new linear operator. Okay, nothing special there. And now what we can do is take the trace. The trace makes sense. Remember, you can define it with respect to a basis, and then you have to show that it doesn't depend upon the choice of basis. It's because the choice of basis matrices can be flipped around because the trace of AB is equal to trace of BA, then your U and U inverse cancel, so your trace doesn't depend upon the choice of basis. And this is what you're doing here, okay? And this is a bilinear form, but it's symmetric and it's L invariant. Symmetric you can see, okay, because it's just the fact of the trace. The trace of AB is equal to the trace of BA, standard result in basic linear algebra. So it's clear then that if I put one or the other, it doesn't matter. So this one here is easy. The L invariance is what you should check. Not that difficult either, but you should check it. That's the exercise. So this is great. It means that from any representation, we have a corresponding bilinear form, symmetric L invariant bilinear form. Not necessarily non-degenerate. This does not follow in general. That's why it's not there. But symmetric and L invariant, yes. So we have as many bilinear forms as we have representations, at least. Okay, good. Let's recall, I don't recall if I defined these in the earlier lectures, but let's define them again. If I have, we'll just call it a refreshing of the definitions in your mind. So a representation of the Lie algebra is said to be irreducible if the only L submodules are V, the representation itself, and, sorry, this is a typo that shouldn't be here, or zero, okay? There's nothing else. There's no other invariant subspace with respect to the representation. It means it's irreducible. It's somehow a solid block and you can't break it up into smaller parts. There are no subparts inside it that are non-trivial. And a representation of L is said to be faithful if the map rho from your Lie algebra V to the endomorphism ring of V is an injective map. Okay, that kind of means that, well, it means that you can identify L with rho of L inside here because it's a linear isomorphism. In fact, it's an isomorph. The map rho gives us an isomorphism of Lie algebras between L and the image of L inside here. Kernel is zero. It's an injective map. The kernel is zero, so it will be an isomorphism. So allowing us to identify it. Think of it almost as an embedding of your map L into the linear operators, or with respect to a choice of basis, the matrices. Okay. So now let's prove our first result. What we're going to do here is go back and use the results that we one of the results that we proved in last week's lecture, in the previous lecture. Okay, so let V rho be an irreducible L representation, irreducible in the sense we just defined. Then we claim that there exists a linear map from the radical of L to the field K over which we're working, such that any element in the radical acts as multiplication by lambda of x. Okay, so it means that if your representation is irreducible, the restriction of the representation to the radical actually is forced to act in a very simple way, completely described by one particular linear functional into the field. So let's see how we might prove that. What we're going to do is use Lee's theorem from last week. Okay. So since the radical is by construction solvable, Lee's theorem tells us that there exists a v, small v sub 0 inside in V, which is a common eigenvector of all of the elements of L, the radical of L. Okay. So the radical is the maximal solvable ideal, hence we can definitely apply Lee's theorem, and we find one of these common eigenvectors inside there. Okay, now this means, equivalently, this is an observation, I guess an easy observation we've been using a lot, but let's write it out, let's spell it out slowly again. Equivalently, this means that we have a linear map that goes from the radical to the field. Sorry, this should be mathfrak B. This is the field, that's a typo. Such that x operates in V0 as lambda x by V. Okay, that's what it means to be a common eigenvector. Remember, the only trick that was here was to actually spot that defining L in this way actually does give us a function. You need to check that it's linear. That's the only thing that's really going on in this observation. Now, from this lambda, let's produce a space. Let's sort of enlarge the space from V0 to the largest space possible for which this identity holds again. Okay, so for which, let's look at all of the elements inside in V such that x acts according to this recipe here. So V and the linear span, the one-dimensional space spanned by V sub 0 is definitely contained inside here, but it is possible that it could be larger. Okay, but we're just looking at the largest one that satisfies this identity. And in particular, though, we need to ensure this is non-zero because we have one of these vectors, V sub 0 inside there. We used the same argument last week. But what we know now from such sub-representations, what we know is that it's actually an L sub-representation. Every element of L will not act like this. That's not guaranteed at all. But what is guaranteed is that this thing's closed under the action of L. Okay, that was a result we proved last week as well. You can go back and check. A very useful result. But now, okay, remember we assumed that the representation is irreducible. So that means that this is an L submodule of V. But it's irreducible, so the only submodules are 0 and the whole space itself. We've observed that it's not 0. It can't be 0 because V0 is in there. Therefore, the only other option left to us is that it's the whole thing, is that it's V. Hence, we must have this. But that means that every element inside in V satisfies this identity here. Just to say, this thing here, the elements which satisfy this condition are actually everything. And that's exactly what's stated up here. So once your representation is irreducible, the radical acts in this. Every element is like a common eigenvector of the for the radical. Okay, a very useful result. So this is a lemma. What are we going to prove it for? Well, we're going to prove a proposition from this. But first, I'm going to give you a technical exercise that's needed inside the lemma. But we'll just take it out, leave it as an exercise to you so that the proof of the lemma is, so that you get a feeling for what's going on. This basic linear algebra is all that's happening here. So we take an L representation, where let U be a submodule, and we denote the associated representation by, which is to say, just, you know what I mean, the restriction of the representation to U. We denote that by this pair here. We can also form a quotient representation. Whenever we have a submodule, we can quotient the representation by the submodule and get a new representation, which we denote by this. Now, what you should show is that both of these are representations. And what we saw was that every representation has an associated bilinear form constructed using the row of the representation and the trace of in the linear endomorphisms on the corresponding space. So this makes sense. That's the bilinear form associated to this representation. This is the bilinear form associated to this representation. And the sum of two bilinear forms is again a bilinear form. So we've got a bilinear form here going from L cross L into K, and we have a bilinear form here, a sum of two other bilinear forms going from L cross L into K. We want to see that two of these things are equal. So you see the identity here is certainly well posed. And you should show this. The hint here is that you consider the linear isomorphism. Of course, we have an isomorphism of vector spaces here. And try to show that with respect to this isomorphism, the trace here is actually going to be given on the other side by the sum of the trace of this and this. Okay.